I've got a lot of slides, so I'm going to go fast, and I might skip some slides. Okay. I'm a particle physicist, programmer, and aspiring data scientist. I spent about 10 years doing software development, working on developing a multi-stage cascade classifier that processes massive data in real time. I was part of the team that helped discover the Higgs boson. That might sound impressive, but those are a lot of names on the paper. I now work on using advanced machine learning techniques to do identification of subatomic particles based on their decay properties. And I'm going to talk about how switching to R's made it easier for me to do a lot more than I would have been able to do otherwise. So particle physics is the study of subatomic particles and the fundamental forces that act between them, and is basically, we're trying to address the question, what is the universe made of? We have a very successful theory that's developed sometime around the mid to late 20th century, but there's still lots of questions that are unanswered. So to try and probe these mysteries, we built the Large Hadron Collider, which looks like this. So this is in Geneva. This is 27 kilometers in circumference, 9 kilometers across. You see the Lake Geneva in the background there. This is all buried about 100 meters below ground. Okay, and it costs about $10 billion US. So what happens is we inject protons into a number of particle accelerators that each time they go around in the circle, they speed up, they build up more energy, and eventually these beams of protons collide inside one of these detectors like this here, and right, boom. Okay, so the way that the data is collected, because all of this endeavor, all of this blood, sweat, tears, money, the end product of it is data, okay? So how this works is after the data is collected by an experiment, there's some online filtering that happens. This is then transferred to the computing grid. Top level of that, half of that is here in Budapest, just up in the Buda Hills. Then it goes to lower levels, and eventually users can then send their analysis jobs to the grid where they run. They get back their results, and then they can turn these results into a plot on paper. So the data analysis software that we use is called ROOT. We've been using it for about 20 years for a lot of particle physicists. It's the only data analysis software that they've ever used. Command language is a kind of pseudo C++. Now Python as well, about a third of the community is using the Python command line interface. You either work interactively or using macros on small data, or if you've got big data, you compile with root libraries and send your job to the worldwide computing grid. Root really excels with big data. It has a data format that's optimized for large data sets. This is where it does really well. However, writing complex algorithms is really difficult to do it interactively. You end up writing really huge C++ programs. There's a lot of tweaking, endless edit compile loop that you go through. Also, the root developer's vision of what constitutes good data visualization is somewhat differently aligned from that of the average particle physicist. This is from the official root project statistics page, and this is meant to convince you that since all of these other people downloaded root, then you should too. Well, okay, it's lovely. With a bit more work, you get a plot like this, but there's a lot of tweaking in order to get to this stage. Cool thing now is that there's an R interface to root, so you can now call R functions from root. But I don't know anybody who actually does this. It was something developed by a student in the Google Summer of Code last year. So if you wanted to do a fit, this is how you would do it. There's a lot of code there. You could scroll through it. There's about 100 lines of code there. There's a lot of typing. So for machine learning, we have a piece of software called TMVA, which is the toolkit for multivariate analysis. There's an interface to R, so there is now this thing called TMVA, which allows you to run R's machine learning tools from TMVA. So this is how you would train and evaluate a decision tree using RMVA. And, well, there's a lot of code. This begs the question, is C++ a good choice for data analysis? Should you spend days coding something that runs in minutes, or perhaps write something in a couple of hours that will run during your lunch break? Which of these strategies is going to get you to your answer faster? So R is a language that places a high value on development time rather than runtime, so it means less typing for the user, which is good. And I like this quote by Larry Wall, who was talking about a number of lines of code needed to accomplish the same task using different languages. You can eat a 1-pound steak or 100 pounds of shoe leather, and you feel a greater sense of accomplishment after the shoe leather, but maybe there's some downsides. So I chose R simply because I wanted a tool that I could work with and not have to fight against. It was very easy. It's very easy to express what I want to achieve. There's a huge number of packages, really great community. If you get stuck, it's very easy to get answers to your questions. You get really nice plots that require very little tweaking. It's fun to work with, and I haven't needed to use Root for a year. And for me, that just means I'm happier. It's just easier to work with. So my analysis is identifying particles based on their decay properties. In these particle physics collisions, proton-proton collisions, particles called quarks and gluons are produced copiously, but we don't observe these individually. Instead, we only can see their decay products. What we observe is a cone-shaped spray of particles called a jet, and these measured particles are clustered by a jet algorithm, so you should think something like k-means. And the resultant jets are viewed as a proxy to the initial quarks and gluons that we can't measure. So if you want to just see sort of conceptual picture, you have two protons coming in, colliding, and you have either quarks or gluons coming out and then decaying to produce these sprays of particles that we can actually measure. And here's what an actual event looks like in a real detector. This is a 6-jet event. So the problem, in a nutshell, is that beams of energetic protons collide in the detector. We get quarks and gluons coming out, and we have algorithms that then reconstruct these as jets. And we'd like to know for each jet what initiated it. What was the thing that it decayed from? Was it a quark or gluon? And this would be very interesting because a lot of interesting stuff decays to quarks and a lot of boring stuff decays to gluons. So this would be a good way of getting a handle on backgrounds for sort of different new particle searches. And this is something that machine learning could be useful for. Machine learning's been around for a while, but there's been a lot of skepticism about machine learning in the community. I know in 2010, there was a quote by a senior physicist who when talking about machine learning, said, "You'll run that over my dead body." So some people have some very strong feelings about machine learning in particle physics. We've used artificial neural networks, but now boosted decision trees are kind of a favorite thing now. So the data production pipeline here is I have some simulated data into which I insert my own handcrafted features, and I attach ground truth class labels to each jet. An interesting thing about this machine learning problem is that there's not a very, it's not straightforward how you do this. So in fact, there's a significant amount of label noise, mislabeled jets. And some jets can't actually have a label assigned to them, so then there's jets with no label. And we write out the data, and then there's a package that's been around for about 10 years that allow you to then import this from root into R. I use data table and dplyr somewhat equally. Data table is really fast for importing data and for doing sort of fast filtering. dplyr is really useful for what I call data analysis dematryoshkification, which if you've used dplyr and you know Russian nesting dolls, you'll know what I mean by this. And it kind of mirrors the way that you think about processing data, like on a production line, separate tasks you hand the object from each stage. Great, okay. So SAW, this is a really nice package, but I don't know if many people know about this. This allows you to cache objects on disk, and it frees up memory. So this really helps you stop running out of memory space. I use Caret for a lot of things, for a lot of data munging, so you can do things like apply a cut on correlation between features, and this really slims down the feature space quite considerably. I'm going to skip that, and that, and that, and okay. So for looking at correlations between features, QGraph is a really nice package. This is where each of these features is represented a node on a graph. These nodes repel, but they're held, they're attracted towards each other by kind of a spring with a spring tension that's proportional to the Pearson linear correlation between features. So this allows you to kind of see the correlational structure in the data and which features are sort of correlated with each other and which are not. And this was very useful for seeing what kind of features might have similar sensitivity to common physics. So to try and explore the data, I reduced the feature space to a lower dimension. Here I'm using PCA and I'm plotting the first two principal components. And this is a covariance biplot, so the idea is these are the loading vectors. The loading vectors have a length which is proportional to the standard deviation of the features, and the angle cosines between them gives you an approximation of the covariance between the features. And overlaid on top of this, I've got a 2D kernel density estimate for the distributions of quarks and gluons. So that is a good way of sort of summarizing a lot of information about the data. I also tried using t-distributed stochastic neighbor embedding, but this wasn't really that helpful for picking out any hidden structure that might be in the data. I also used a deep learning autoencoder with ICA whitening. This was implemented using H2O. It's shocking how fast this is. I really didn't think that I'd be able to get something out of this on my hardware. I've got very modest hardware, but this runs in just a few minutes. So it's very impressive. I'm definitely going to be checking out more of H2O's features. Feature ranking. I want to be able to see which of my features are most interesting for this particular problem, but I've got modest hardware, so I need a fast way of doing this. The method that I used was based on an entropy heuristic. It's a filter-based method that involves ranking by information gain, which is the metric that is used for building a decision tree. And the basic idea is I rank by information gain and do this repeatedly for a large number of bootstrap resamplings from the data and then average. And this gives me a non-parametric estimate of the mean for each of these feature importance metrics and a confidence estimate for that interval. You know what I mean. Okay, sorry, there's a lot of information on here, and yeah. To the right is good features, to the left is not so good. And okay, those are good features. I won't go through that. So this is kind of my summary slide. It's often said that about 80% of data analysis is spent on data munging, and this was certainly true in my case, but R has helped tremendously. All of my analysis has been done within R entirely, and the journal paper is being written in R Markdown. So this is a first. This workflow has enabled me to develop the analysis interactively and keep track of what I've been doing, but also it gets me a document that in a simple one-step process I can render the final document for publication, which is really nice. This means that the analysis is completely reproducible. R Markdown plays really well with version control systems, which is good for collaboration. To the best of my knowledge, nobody has done this in particle physics before. So R really has enabled me to do far more than I could have achieved using only standard tools available to particle physicists. It's been a huge help. And that's my final slide. So that's my cat, one of my cats.
Thank you very much. Very good presentation, but you are also doing very good with time management. So we have time for a question you would like to ask. Yep.
Yep.
Are you trying to tell your colleagues that this workflow is good? And if you are, then what do they do? How do they react?
Okay, so as I said, about a third of the community are kind of using Python, and they just started getting into using IPython notebooks, and that's become a kind of popular thing, but it doesn't really play very well with version control. R Markdown is kind of nice, especially with a new version of RStudio, which allows you to do notebooks. For those people that like Python, there is a package called Nitron that allows you to run IPython in code chunks within an R Markdown file. And then if you use something like a Feather, then you can have an IPython code chunk, transfer the data into a Feather file, and then read that into a subsequent code chunk which runs R. So you can mix and match. So this could be something potentially interesting to the particle physics community, that you could use the best of both worlds. Yeah.
You mentioned very briefly that you were using a saw to get around the RAM issues.
Yeah.
Could you expand a bit on how that actually works? Does it write a whole new set of data and then pull it up, or does it operate?
So I don't know how it works behind the scenes, but it's just magic. You store an object, and then you can still access it and perform operations on it, but it's not in RAM. Now, if you then modify that object, then it comes back into RAM, and you have to remember to store it again. But you can perform objects on it, and it's not in RAM, so it just gives you a lot more space to work with. It's nice.
And last question from everyone.
Our two speakers today talked about Feather, and we indeed also use it, and it was pretty quick, much quicker than data frames, but we also saw that the disk size blew up quite a bit, like a factor 5 or 10 bigger on disk, these files. So did you also see something like that, or is it something just the same size?
I've played around with Feather a little bit, and I've seen how it could be useful for sort of chaining together sort of IPython and R code chunks, and that could be something interesting, but I haven't really done a lot with it.
Right. Okay.
So, it's not something I've spotted.
Okay, let's thank Andrew again.